Okay, so I asked you to go ahead and try to do the mean and the standard deviation for each of these probability distributions. So wanting to remind you that when you are showing your work, that you can just show the first couple of terms, or even just like the first term and then the last term in order to show the work. What do you get for the mean of x? 14.65. And what are the units? Units. This is just the number of units for number one. We're talking about the number of units that a full-time student is taking at the community college. And then the standard deviation. So remember that this is going to be the square root. And if I was going to show the first term, I'd have 12 minus 14.65 quantity squared times 0.25, and then dot, dot, dot. What do you get for the standard deviation here? 2.06 would be correct. Also in units. Okay, so if you were going to interpret them, so to interpret the mean, we would say something like this. If we randomly selected, are we just randomly selecting one? Many, yes. So many, some would say many students from this community college. The number of units taken will be 14.65 on average. Okay, be really careful when you do the interpretation. This is also known as an expected value, but I don't want to say the expected value is 14.65. I don't want to use expected value as a way to explain or interpret expected value. So this is how you would explain it in sort of simple notation. Okay, now the standard deviation is about how far away our stuff is varying on average or typically. So I'll write that one down here. The number of units taken by a randomly selected student at this community college typically varies from, by 2.06 units from the mean of 14.65 units. Okay, so for the next two situations, we're trying to calculate the mean and the standard deviation as well. Here we're taking the random variable x and we're multiplying it by 50 so that we get a tuition. So the mean of t, what does the mean of t end up being? Did anybody get that far? 732.5. And what kind of units is this? Yeah, this is in dollars. Okay. And how about for the standard deviation? 102.8. And also in dollars, so $102.80. How about for situation 3? We have the overall cost. So there's a flat fee of $100 per semester, and then you have whatever your tuition is based on the number of units that you have. So the mean of C, did anybody get that far? 832.5, also in dollars, since we're talking about cost. And standard deviation of cost is 102.8. Sorry. Okay, So before we get really involved here, I do want to talk about a couple of little tips for you on your calculator. Hopefully you noticed that the probabilities are the same for all of these situations, but the random variable is changing. We've got x and then t and then c. Okay, the first thing I want to show you today is just like if I was going to be doing this part on the calculator, just reminding you that one of the easiest ways to do it is to put your data into some lists and then use your list operations in order to do the computation. You have to show some semblance of work. So if I was going to show my work here for the standard deviation, I would write what I wrote here, but then when it comes down to doing my calculations, I'm going to just type it all in. So the square root, and then I'm going to go to my sum, and then I'm going to take my values, which are in L1, minus the mean, which we just computed, quantity squared, times the probabilities, which are in L2. Oh, what happened there? Hold on. Square root, sum, L1 minus 14.65. Oh, I know why. I need another parentheses here. What is that? Oh my god. Okay. L1 minus 14.65 quantity squared. Oh, quantity squared. Oh my god. Okay, we'll try this again. I can do it. Okay. Sum quantity L1 minus 14.65 quantity squared times L2, close parentheses. Okay, double check. So values minus the mean squared times the probability, and then we're going to find the sum of all that, and then square root. Oh my gosh, okay. Yay! Okay, whew. Yes?
So how would you use the standard deviation thing? Like, if you go to go to where you found the sum, and then there's the standard deviation?
That's if I have data in a list, and I want to just find the standard deviation of that one list. Here we don't just have a list of data. Here we have a probability distribution where we have weighted probabilities. So if I go to number 7...
So is there any way to make it weighted?
No. No, not using this calculator operation. No. Okay. I do want to show you something else that's kind of cool. If you notice that, so here we have to type this sequential numbers. Hi. I'm good.
You're busy right now.
I'm super busy right now.
Yeah, I was just going to say thank you for your help yesterday.
Oh, okay. Thank you for your help yesterday. Okay. Okay, so here we have a sequence of numbers. Does it get annoying to have to type in 12, 13, 14, 15, 16, 17, 18? Okay, well, so let me show you something cool that you can do. If you have a sequence of numbers, you can have the calculator input that sequence for you. Okay, if you don't want to know how to do this, or if it's confusing, or you're just too overwhelmed by all the other things that we're learning right now, you can just space out for a second. If you would like to know how to do this, let me show you how. So I have a sequence of numbers here from 12 to 18, and the step is by 1. So I'm going to go to the header. Here, I'll even clear it out so you trust me that this is really happening, okay? So I'm going to go to the header L1, and then I'm going to go to second stat ops. And I want to select number 5. I want to input a sequence of numbers. Oh, that's not what I... My gosh, I'm spazzing out today. Okay, second list, I want to do number 5, a sequence. Okay, so the expression is exactly what is your variable expression to represent this sequence that you have. So I'm just going to call it x. And this part always feels kind of dumb because what's your variable? X. I'm going to start at 12. I'm going to end at 18, and my step is going to be by 1. And so it's going to paste all that in to L1. Okay, now if you don't have that operating system, remember that you would just need to put commas between all these terms. So you type in sequence and then x, comma 12, comma 18, comma 1. hit enter, and it dumps them all in there. So the same thing can be applied for L3 and L4. So I did L3 as the tuitions. So I can go to the header, and I can hit second list, ops 5 for a sequence. My expression is still x. My variable is still x. I'm going to start at 600, end at 900 with a step of 50. And it dumps them all in there. So it's just kind of a nice little shortcut if you have a sequence of numbers that is predictable and can be written as a variable expression. Okay, so back to our problem at hand here. What we're trying to investigate is what happens if I take a random variable and I multiply it by a value, or if I take a random variable and I add a value to it. We've actually talked about this before. We talked about it way back in chapter 1 when we were talking about transforming linear transformations of data. So our original random variable had a mean of 14.65 and a standard deviation of 2.06. We then created a new random variable, which was essentially what we call a transformation of my other random variable. I'm multiplying 50 times the random variable x. Well, hopefully it's not going to be much of a surprise to learn that if I take the mean 14.65 and multiply it by 50, I get 732.5. It's kind of exciting, actually. So what that means is that you didn't have to find the mean of this random variable by taking 600 times 0.25 and then plus 650 times 0.10 plus this times this plus this times this and all of that. So if I know that I have a random variable that is a transformation of a previous random variable, we could have just multiplied 14.65 times 50 to get the new mean. Is it the same case here? If I take 50 times 2.06, do I get 102.8? Yes, okay, great. So that alleviates having to enter all this junk into L1 and then doing the calculation with my lists. If I know that this is a linear transformation, I'm multiplying, then that's going to just be a multiplier for the mean and the standard deviation. So think back when we talked about this before. If I take a set of data and I multiply all the data values by, say, 5 or 50, as in this case, will the mean change? By what factor? Yeah, by a factor of 50. If I take that same distribution, I multiply all the values by 50, what does that do to the standard deviation? It changes it as well. Yeah, by a factor of 50. So there's nothing new in terms of concepts today. What's going to be new is just all the notation that we use. We're using all these subscripts, and we've got mu sub x and sigma sub x and mu sub t and sigma sub t, but the concepts are really the same. So here, if we go to the next situation, we had x, which turned into t, which was 50x. Right? We know that the mean of t was 732.5, and sigma sub t was 102.8. We made a new random variable that was 100 plus t. So if I take a distribution and I add 100 to all the values in the distribution, how does the mean change? You add 100. If I take a distribution of values and I add 100 to it, to all values, does that change the standard deviation? No. So again, not a new concept. We're just seeing it in a different representation. So on the back side, we're going to generalize what's going on. What are the effects? You can make your own notes here at the bottom if you'd like to. So when you're ready, go ahead and turn the page. Okay, so what is the effect of multiplying or dividing by a constant? Multiplying or dividing by a constant changes which values? Does it change the center? Yes. Does it change the spread? Multiplying or dividing? Multiplying and dividing changes the center and the spread. What about the shape? If I take a distribution of values, so let's see, we have a distribution of values here. If I plot, let's say, L1 versus L2, so this is going to be the probability histogram for the x variable, zoom 9. So, okay, well, here's a crappy representation of that. Let's go by, say, like 2s. Okay, well, here's the distribution. Okay, well, so then what we did is we multiplied all the values by 50. So that turned into L3 versus L2. Let me change my window here slightly by, say, does it change the shape of the distribution? No. Okay, so the center and the spread change, but the shape is unchanged. That's going to be important in just a second. Okay, so what if I add or subtract a constant to a random variable? Does it change the center? Yes. Does it change the spread? Not the spread. What about the shape? No. Okay, so let's write this in a little bit more like formal way. What is a linear transformation? And how does a linear transformation affect the mean and the standard deviation? Okay, now we're talking about random variables. If I have a random variable, let's call it y, which is a linear transformation of random variable x. And remember that a linear transformation can involve an addition and or a multiplication. It could just be an addition, it could just be a multiplication, it could be a combination of both. If y equals a plus bx is a linear transformation of x, then I can compute the mean of y. I can do it algebraically. I can write mu sub a plus bx. And then I have to ask myself, does adding something to the mean change the value of the mean? Yes. And does multiplying something by the mean change the mean? Yes. 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 So if I want to find the mean of y, this new random variable that I've just created, I can take the old mean, multiply it by b, and then add a to it. I can also calculate the standard deviation of y. I can write sigma sub a plus bx, and then ask myself, if I have my random variable and I multiply it by some value, does that change the standard deviation? Yes. If I add something to the random variable, does that change the standard deviation? No. So I don't put an A here. A doesn't have an effect, but B does. And I have to be careful because this could be like A minus B. If it's negative, I want to make it be positive. Doesn't make sense to have a negative standard deviation, does it? No, doesn't make any sense. Okay, so then what about the variance? Any guesses? B squared, sigma squared sub x. So I just want you to take a deep breath, okay? We haven't really talked about anything new. The only thing that I feel is sometimes tricky for students is just the notation. But we really haven't talked about anything new here. So let's go through an example, and you're going to see how everything that we've talked about already will be in this problem. Okay, so in a large stats class, the distribution of x, so capital X, it's a random variable, are representing the raw scores on a test. It tells us we were normally distributed. Okay, so automatically I'm thinking like, ooh, okay, normal distributions. All kinds of stuff we talked about in Chapter 2, and we reviewed on Monday. Given a mean and a standard deviation of this normal distribution, the professor decides to scale the scores by doing some multiplication and some addition. Okay, so first I like to just kind of write down what's going on in the situation. So X are the raw scores. And I'm being told that I have a normal distribution with a mean of 17.2 and a standard deviation of 3.8. Okay, so remember that if I was just talking about a list of data, we would write n, and then we would write mu, comma, sigma. So I'm not doing anything different here, except now that I'm specifically talking about the mean of x and the standard deviation of x. So I want to make sure to use my descriptive subscripts just to keep things straight for myself. Okay. So in part A it says define the random variable y to be the scaled score. And then do some stuff. So can you write y as a function of x? Can you write a linear expression that will represent y in terms of x?
Yes.
What would you say?
N plus 4
X. Yeah, it just says multiply the raw scores by 4 and add 10. If you want to write 4x plus 10, you could write that too. So, not supposed to be tricky here. Can we find the mean and the standard deviation of y? The mean of y, you can just do a substitution, 10 plus 4x. Okay, this part is really optional right here. Okay, I'm making sure to show all of my notation so that if you go back and look at it, and there's a lot of people that were absent in fourth period, so these notes are for them too. So you can go back and look at this and really understand where it's coming from. Okay, so then I'm going to ask myself, if I add, does that change the mean? Yes. If I multiply, does that change the mean? Yes. And so this is how I'm going to compute the mean of y. Okay, you can really skip this step if you want to, okay, but I really want to make sure that it's clear where it's coming from. And so now we're just going to say 10 plus 4 times the mean of x is 17.2. And so then we just compute that. It's just a bunch of algebra. And really, this isn't algebra. This is just math. What do you get? $78.8. Okay. Standard deviation of y, so sigma sub y, is sigma sub 10 plus 4x. Does adding affect standard deviation? Does multiplying affect standard deviation? So this is going to be 4 times sigma sub x, which is going to be 4 times 3.8. And so this is why I'm saying, like, if you label everything, then all you have to do is just look up here and plug stuff in. What do you get? 15.2. So then for part B, what is the probability that a randomly selected student has a scaled score of at least 90? Probability, scaled score, at least 90. Which inequality symbol should I put here? Greater than or equal to. Okay. How will I do this? A normal distribution. Do we know if the distribution of y is normally distributed? Why? It doesn't say y is. It says that x is. It says X was normally distributed. Does that imply that Y is?
Yes.
Why?
Shape is
Yeah, because shape is unchanged with any transformation. If I started with the normal distribution and I transform some stuff, I still get a normal distribution. So you might want to just make a note about that. Y is also normally distributed. And the reason for that is because we just had a linear transformation of a normal distribution. Okay, so some of you are good and can just go straight to the calculator, and some of you don't want to remember the calculator stuff. We're going to have 13 different inference tests to learn in second semester, so there's going to be a lot of calculator stuff you have to know. So if the norm CDF thing sort of falls out of your mind in second semester, that's okay. Let's remember how you would go about doing this problem. It's just a z-score. So I look here, I'm like, okay, normal distribution, oh, wrong page. Normal distribution, I see z on there. Oh, okay, I need to turn it into a z-score. So that's my own little reminder. What would I put in here? Some stuff? Yeah, what numbers would I put there? 90 minus 78.8 divided by 15.2. This is going to turn into a z-score that is positive 0.74, and then I can go to my table and find this value. Okay, so you always have this fallback. Yes, of course, you can go to the normal CDF. But if you forget, if you're not sure, you can't remember how to get there on the calculator, remember that you still have your formula sheet. Normal distribution means table A means z-scores. Okay, if I'm going to do it as a normal CDF, I would enter what? 90, comma, 1,000, some big number, then 78.8 and 15.2, making sure to label everything. This is my lower value. Here's my upper value. This is my mean of y, and here's my standard deviation of y. If I calculate that, I get a slightly different number, but really, how different are they? In terms of a percentage, they're both roughly 23%. So let's remind ourselves what this means. There is about a 23% chance that a randomly selected student has a scaled score of at least 90. So again, just a reminder that there's really nothing new. The only thing that is feeling new is just the notation. We're just putting little subscripts by everything. Okay, I'm going to hand you an activity, and we're going to start the activity together.